So in chapter 9, we're going to start talking about rotational motion. Very similar to how we talked about linear motion in chapter 2. We'll talk about things going in a rotating pattern and a circular pattern is what we'll actually talk about for rotational motion. So our goals for this chapter are one, to study angular velocity and angular acceleration, and actually angular displacement as well. And then we'll look at some rotation with constant angular acceleration. And we'll also discuss the relationship between a linear quantity, like a linear velocity or a linear acceleration, and its rotational counterpart, like a rotational velocity and a rotational acceleration. We'll also talk about the kinetic energy of an object that's rotating, as well as the object's moment of inertia. So what is rotational motion? Well, rotational motion is just exactly that. It's some sort of motion that is rotating. It's going in some sort of constant pattern around some fixed axis here. So the rotational motion we'll focus on in this chapter is just circular rotational motion, which something is rotating in a circular pattern. Just like you have here, this ride at a circus is rotating around this center axis here. This is the axis of rotation that it's rotating around, and these people are going around the center of this as the entire thing rotates around, probably in this path like this. So some examples of rotational motion: you have a top spinning, which has rotational motion. It has some axis of rotation that runs through right here. This would be its axis of rotation. It's rotating about that. It's about some tilted axis here. We also have a windmill, which also is in rotational motion. Its rotational axis would be straight through the back of it, so the propellers are rotating perpendicular to its axis here. You also have a rotational motion in the solar system. There's actually a couple types of rotational motion here. You have the planets are going around the sun. This is sort of an elliptical pattern, actually. But you also have the planets are rotating on their own axes as well. So that's rotational motion there as well. You can see this axis of rotation, for Mercury is perpendicular, Venus is there, Earth is, obviously we're off to a slant right there, so is Mars, right? Those are the axes of rotations of those. It's simply the stationary point in which it rotates around there. We can also talk about maybe something more that we'd see every day is the rotational motion of a bicycle tire, or sometimes this is also called angular motion. Rotational motion, angular motion are one and the same, but we have this wheel here that's rotating around counterclockwise like this, and it has an axis of rotation through its axle here, and that axle through the spokes transmit the rotational motion to the edges. We also have rotational motion in things like figure skating, right? You have this figure skater is rotating in a circle around, so she has some fixed axis. This is actually where her center of mass is, and this is her axis of rotation straight through her. So she's spinning around in a uniform circle about this line. We can also put a couple motions together. We can include rotational motion with another form of motion, like projectile motion. If we have someone diving off of a diving board, he not only has this projectile motion that we studied in chapter 3, but there's also, if he's diving or doing some sort of flip as he jumps, he also has rotational motion as he rotates through. Obviously his head was pointed up and now his head's pointed down, so he must have rotated as well. His axis of rotation is through the center of his body here. That's where he's rotating through. Now, in rotational motion, at least in this chapter, we'll be focused on rotational motion of a rigid body. So imagine we have this object right here that is here's our object. It's in its initial position right here, and it's going to rotate about this fixed axis at point O, right here. It rotates through here and it comes up to some position over here, and then continues rotating up to a position over here, etc. Right? And then this is the third outline. So it's rotating through around this axis in a counterclockwise manner. So we first off, we talk about only the rotation of a rigid body here, and what I mean by a rigid body is that it's any object in which each part of the body is fixed relative to each other. So what that means, basically, it's not gelatin at all, but it means that if a point right here rotates through, then the distance, and another point right here rotates through also, then this distance between them actually remains the same, right? So I have my point there and I have my other point here, and it stays in the same exact position, has the same distance here to the edge as it did here, the same distance here, same distance over there, and the same distance here. They didn't move relative to each other. That's what we mean by a rigid body. Think of like a steel plate or something like that, when you rotate it, the plate itself, the steel in the plate doesn't move. It's just the entire plate moves as one whole thing. How far this is moved is defined, we'll talk about this more in a minute, but we define how far it's moved by this angle theta. Instead of talking about a linear displacement here, we'll actually talk about an angular displacement, so that this point P rotates through some angle, right? And also some other point over here would rotate through the same angle. Regardless, anywhere on this line, everything's rotating through the same angle. Whether it's a point P or some other point over here, it rotates through and has the same angle. If I move up to another angle here at 90 degrees, then this point P is at 90 degrees, and also this other point over here would be at 90 degrees as well. Okay, so the entire line rotates the same amount, the same angle, and all the particles stay in the same relative position. And we define this angle theta off the positive x-axis, and actually we'll talk about it more in a minute, but if the angle is counterclockwise, then this is a positive angle measure. So rotational motion is analyzed very much in the same way that we analyze linear motion. And so you're going to start to see a lot of the same equations that we've seen before, simply with some replacement, in which we'll define things in terms of their angular quantities instead of their linear quantities. The key difference here is that we have everything is moving in a circular motion about a fixed point. So it's going to be a little bit rough. So here we have circular motion about a fixed point. It's going to be a little bit rough to talk about something moving linearly, or the distance that it moves when it's rotating around in a circle. Now, if we go back to the previous slide here, then we can see that obviously this point here has rotated a further distance than a point, say, right here. This one is only going to cover some tiny little distance right here, whereas this one will cover a much larger distance, but the angle will be the same. So it becomes a little bit difficult to talk about the distance something travels because the distance is that's different depending on where we are on the object. So we instead of determining things or defining our quantities in terms of absolute distance, we'll revise them so that our quantities are now given in terms of a angle. And so we have a angular displacement. So instead of a linear displacement, a delta x, we'll consider an angle, theta, or more specifically, we'll consider a change in angle, or a delta theta, for rotational motion. And that's really the key difference between linear motion and rotational motion. Now, partly because the motion that we've looked at for the most part has been linear motion before, and partly because we'll simply care about how rotational motion translates to linear motion, it's convenient for us to define a angle that is tied to some length at which the particle would travel on its edge. So we do this by defining the radian, or using the radian to define our angles here. So the radian is defined as an angle measure, this is 1 radian, in which the radius is equal to the arc length which is past s, right? So we have here, this is the distance that a particle would travel along the edge, that's given by s, and when that s is equal to the radius, then that is defined to be 1 radian. So we have basically the angle theta would be a ratio of the distance a particle travels over its path, s, divided by its radius here. Or more conveniently, we could say that the distance the particle travels is the radius times the angle theta, and that's only when the angle theta is measured in radians. So if we're given an angle in radians and given a radius, we can find out how far it travels. And you can, we'll play around with some radians here in a second. But that's the definition of a radian, so we can get this nice relationship in which the length something travels is the radius times its angular displacement, theta. So if we're going to be using radians, we need to be able to familiarize ourselves with what a radian is. Probably, well, actually, most of you guys have probably heard of radians before, but you still probably think of things in terms of degrees a little bit. So let's just do some common conversions. We have here 1 radian is about equal to 57.3 degrees. That's just what it happens to be. Or we can say that in 1 circle, in 1 full revolution, which is 360 degrees, that is 2 pi radians. And you can see that from, the circumference of a circle is 2 pi r, right? So if you were to plug in the circumference for s, 2 pi r, and make that equal to r theta in the previous slide, then you'd see that 1 full revolution is 2 pi radians, or 360 degrees. So if we convert just some common angles, just to practice our conversion between degrees and radians, we have 45 degrees times 2 pi radians divided by 360 degrees, because 2 pi radians per 360 degrees. And we should end up with pi over 4 radians, which is the same as 0.785 radians. Same thing with 90 degrees. Take 90 degrees times 2 pi over 360. We end up with pi over 2, or 1.571 radians. If we talk about 1 entire revolution, well, that's 360 degrees, right? So that converts to 2 pi radians, or 6.283 radians. If we have 2 revolutions, that means that it goes around twice, right? So I'd have 2 times 360, or 720 degrees, or 2 times 2 pi radians, we'd have 4 pi radians, which is 12.566 radians. And if we had see 30 revolutions. We take 30 revolutions times 2 pi radians per revolution, so we get 60 pi radians. If we had 100 revolutions, then we'd have 200 pi radians that the angle went through. So remember that we're going to want to talk about the angle that something travels through. So we'll define that as the angular displacement. So that's defined as the angle at which an object rotates through over some time interval. The units we'll use for this are the radian, and remember that every point will undergo the same exact angular displacement. So a point here goes from at time t1 to time t2, goes through some angle delta theta here, but also some point down here that rotates through to this line, or this point right here, also rotates through some angle delta theta as well. So every point on the object goes through the same angular rotation. And we call this angular rotation, this change in angle would be your, this delta theta is your final angle minus your initial angle, right? So, or you could say delta theta is theta 2 minus theta 1. This is going to replace delta x, or our change in position from the chapter 2 material. So two things to really note on here is that our delta theta is simply a change in angle, and very importantly, we need to note that every point undergoes the same angular displacement. So on this body, the 2 points undergo the same angular displacement. Also on this bike tire here, we have a point, say there's a point up here, rotates through like this, or actually this would probably rotate through, if he's moving forward, probably rotate through some angle there. Similarly, a point next to the axle would also rotate through the same angle. The distances, yes, the distances will be different, but the angle will be the same. Okay, so it's an important takeaway from this slide. So if we follow sort of our reasoning from mechanics, or from linear motion in chapter 2, we move from displacement to rate of displacement, right? Or what we call velocity, right? So we'll move from angular displacement, or a delta theta, to a delta theta over delta t, change in angle with time, and we'll define this as our angular velocity. So angular velocity here is omega. This is the Greek, this is the lowercase omega, and this is the angular velocity. So given what we just talked about on the last slide there, which of these, the boy or the girl, would have more angular velocity? Give you guys a second, maybe you can pause it and come back to it, answer that question. Hopefully you guys have said, well, if he rotates around, say this far here, so he does, let's say he does a half circle here. He comes around to a half circle. He's gone 180 degrees, or he's gone pi radians. Well, she would come around and she would rotate this far. Well, what angle is that? That's also 180 degrees, or pi radians, right? So they've both turned the same angular displacement. They've both gone through 180 degrees. And as long as this is a rigid body, so that everything moves at the same time with each other, then the time it took him to go his 180 degrees would have been the same time it took her to go her 180 degrees. So the time would be the same, and the angular displacement would be the same. So the angular velocity is actually the same for both of these. So takeaway from that is when a rigid object rotates about a fixed axis, every portion of the object has the same exact angular velocity. Everywhere on there has the same angular velocity. If we have a point rotating like this, then it has some angular velocity omega, and another point out here might rotate around like this, longer distance, but the angle is exactly the same, so it has the same angular velocity omega there. Every point has the same angular velocity. Even a point over here goes like this. This is the same angle and angular velocity omega. Same thing here, same angular velocity omega. So to throw the equation for angular velocity up here, we have here the angular velocity of a rotating object is just the ratio of angular displacement to the time interval. This is the same definition we use for linear velocity, in which we have some change in angle, delta theta, just theta final minus theta initial, divided by some time interval, time final minus time initial. So this comes down to delta theta over delta t. This is the same equation that we used for velocity. V is equal to delta x over delta t. It's the same formulation. It's just that we're talking about an angle measure instead of a displacement. We talk about the instantaneous angular speed. It's defined the exact same way that we define instantaneous linear speed. It's simply the limit of the change in angle with time as the time goes to zero. So as we get closer and closer to zero time, it becomes instantaneous, right? If we look at it, so our time, our delta time is 1/billionth of a second, then it's pretty much the angular velocity at that very specific time. The units for the angular velocity are radians per second, right? Because delta theta is in radians and time is in seconds. So we have radians per second for our units for angular velocity, or angular speed, as we can call it as well. The sign convention for angular velocity is the same sign convention that we use for the angle itself, because after all, time does not have a sign associated with it. Time is always positive and increasing. And then delta theta, we said that an angle moving clockwise is negative and an angle moving counterclockwise would be positive. So same thing with angular velocity. If something is rotating counterclockwise, then theta is increasing, and so the angular velocity is positive. If so counterclockwise is positive, and we have, if it's moving the other opposite direction, which would be clockwise, then angular velocity would be negative and theta would be decreasing. Just an illustrative example of what I was just saying. If we have a delta theta greater than 0, so our change in angle is positive. So we go from maybe a 30-degree angle to a 60-degree angle. That's a positive rotation, right? Or if we go from 60 to 120, that's also a positive delta theta. So we have a positive omega as well. So counterclockwise rotation is positive. Clockwise rotation is negative. I think I said that right. Counterclockwise is positive. Clockwise is negative. So then the same pattern that we used for linear motion, we said, okay, let's talk about displacement first, then we'll talk about how that displacement changes with time, call that velocity, and then we can talk about how that velocity changes with time, and we'll call that acceleration. So using the exact same formulation we used in linear motion, we can end up with our angular velocity as well. So angular velocity, or I'm sorry, not angular velocity, but angular acceleration, alpha, is the change in angular velocity with time. So that's omega 2 minus omega 1 divided by our time interval, time 2 minus time 1. So that is equal to delta omega over delta t. Again, for our sign convention, if something is accelerating to the counterclockwise direction, we call it a positive acceleration, a positive alpha. And if it were rotating, or if it were accelerating its rotation in a clockwise manner, then that would be a negative acceleration. So you have an illustration here. We had omega 1 was a small angular velocity, omega 2 is a larger angular velocity. So we have, this would be a positive angular acceleration. Again, we have the equations for alpha, the angular acceleration, which units are radians per second squared, because this is in radians per second, and then we divide by time again, so we have radians per second squared, completely analogous to meters per second squared. And the average rotational acceleration is our change in angular velocities, rotational velocities, divided by the time, or instantaneous angular acceleration would be, again, the limit as this time interval goes to 0. So as we get a very, very small time, our change in angular velocity in that very small time interval would be considered the instantaneous angular acceleration. So here's another little pop quiz for you. You might want to answer these 3 questions, pause it and answer these 3 questions and come back to it. But who has greater angular velocity? Well, that's something that we've already discussed, and hopefully you all say in joyful harmony that that they both have the same angular velocity, right? Because they have the same change in angle with the same time, right? Well, who has a greater angular acceleration? Well, if they have the same angular velocities and the same at every point in time, they have the same angular velocities, then their change in angular velocities should also be the same, right? So they actually both have the same angular acceleration as well, right? So we have greater angular velocity, they have both the same, as well as angular acceleration, they are the same for both of these. And I apologize that I cannot write with a mouse very well at all. So both the same. Who has a greater linear velocity though? Which of these, if we look at it in a line, so we know that the linear velocity is actually tangent to the path that it goes around at any given point, and so he has a large linear velocity and she actually has a much smaller linear velocity, right? Because if we consider that in, say, 1 second they go all the way around, the distance he goes is much greater than the distance that she goes, right? So velocity, linear velocity, is just distance, or speed maybe I should say. Speed is just distance divided by time, right? He goes a much larger distance in the same time that she goes. So he actually must have a much larger linear speed. So when a rigid object rotates about a fixed axis, every portion of the object has the same angular velocity, and this actually should say same angular velocity as well as same angular acceleration. Oh, what does the linear velocity depend on? What about linear acceleration? Well, there were a couple things. Both of them, their linear velocities would depend, if it's not rotating at all, right, then they have no linear velocity. So there must be some rotation. So it must depend on omega. the linear velocity must depend on how quickly it's rotating through at some angle, right? But also we said that the guy up here has a larger linear velocity than she does, right? Because he moves a farther distance than she does. So we also note that not only is it dependent on omega, but it's also, I deleted my omega here, it's dependent on omega, but it's also dependent on how far away the person or particle is from the axis of rotation, so the radius r. If there was someone equidistant between here, then the linear velocity, or actually the linear acceleration as well, would be somewhere between her linear velocity and his linear velocity, or her linear acceleration and his linear acceleration. So it's also dependent on how far away you are from the axis of rotation. So linear velocity depends on both of those, and so does linear acceleration. The linear velocity of a point on an object rotating about some vertical axis. By vertical axis, we just mean that so the axis is coming out of or into the page here. It goes vertically through here and it rotates around like this, right? Rotates around and around. So the linear velocity at that point is the distance it travels divided by the time it takes to travel that far, right? So we have the average linear velocity would be the distance traveled, which is a delta s, right? Because s is the distance something travels divided by how long it takes, right? But now we go back to our definition of a radian, and when we define, this is very important that we always use radians for our angle measures, because that's where all of our equations come from. We define the length something travels, s, is equal to the radius times the angle measured in radians. So I can replace delta s with, here with an r delta theta, right? But we also said that delta theta over delta t, a change in angular position divided by time, is actually equal to our angular acceleration, right? Or our average angular, or not acceleration, but average angular velocity. Sorry, this is omega averages angular velocity. So delta theta over delta t would be our average angular velocity here. So we have our linear velocity right here is equal to the radius times the angular velocity. If we talk about the instantaneous instantaneous linear speed, then v is equal to simply r omega. We don't really need the average anymore. Instantaneously, the linear velocity would be equal to the radius times the angular velocity. And this just comes from this simple fact that the speed is distance over time, and just a matter of replacing distance with our distance defined in terms of radians, which is r delta theta. So we have when angular velocity is defined in radians per second, we can find a linear velocity by simply multiplying angular velocity times the radius, or v is equal to r omega. So let's figure out how the linear acceleration also relates to angular quantities here. The angular acceleration it can be actually broken into two components. We have a tangential as well as a radial. We focused on the radial component in chapter 6, and it was always directed towards the center. But now we're going to deal with motion in which we can actually increase how quickly it goes around. So it's going around at first, and then if I accelerate it tangentially, then it's going to go faster and faster, right? So that would be a tangential acceleration causing a change in speed. So tangential acceleration is parallel to the path at that moment, and also parallel to the velocity. If you remember back from chapter 3, if we have an acceleration parallel to velocity, it results in an increase in speed, whereas a acceleration perpendicular results in a change in direction, right? So if we want to do this mathematically, we can say that our average tangential acceleration is the change in velocity divided by a change in time. But we said change in velocity is actually this guy right here, delta v, is actually r delta theta, or delta omega, sorry. R delta omega, the radius times the change in angular velocity, is equal to our linear velocity, right? That's what we said on the previous slide. But we also have a definition for delta omega over delta t, and that is alpha, right? Because we say that we defined previously that change in angular velocity with time is the angular acceleration, right? So simply calling this alpha, we have our tangential acceleration would be equal to r alpha, or the radius times the angular acceleration. And the radius doesn't necessarily have to be the radius to the far point on it. As you can see, this object is right here, and we're just concerned with the acceleration at this point P. If we are concerned with a different point right here, then it would obviously change the radius, and so we would get a different tangential acceleration. We also have the radial component of the acceleration as well, right? And we know from chapter 6 material that the radial acceleration, the required radial acceleration, is equal to the velocity squared divided by the radius, right? So here's our radial component that always points inward, and that is equal to v squared over r. Well, knowing what we know about the velocity, we have velocity, linear velocity. This was a linear velocity. If you remember back to chapter 6, it was a linear velocity, right? So linear velocity is equal to r omega, as we defined a few slides ago. So plugging r omega into v squared here, we get the radial acceleration is equal to r squared omega squared divided by r, which then reduces down to the radial acceleration is equal to omega squared r, or r omega squared. So tangential acceleration is r alpha, and radial acceleration is r omega squared, or omega squared r. And putting everything together, we have the magnitude of the acceleration of the object is going to be it's just vector quantity. So we're just adding vectors together the same way that we've added them for the entire semester, in which we have the magnitude of the acceleration is the square root of the sum of the squares of the components of the acceleration. So it's the square root of a radial squared plus a tangential squared gives us the magnitude of acceleration of the entire thing, which is this right here. This is our magnitude of acceleration. We can also get a direction from it as well, same way we have in previous chapters. So just to summarize all the relationships we just derived as far as relationships between the angular and the linear quantities, we have here the displacement, the distance something travels, s, is given to us as the radius times the angle theta when theta is measured in radians. So this is S is equal to r theta when theta is in radians. The speeds, the linear velocity is the same as the tangential velocity. There is no radial velocity as long as it's in a uniform circular motion here. It's not doesn't have a velocity really towards the center or away from the center, and so everything is the tangential velocity, which is equal to the radius times the angular velocity, or r omega, when again omega is measured in radians per second. And then we have accelerations. The tangential acceleration is the radius times the angular acceleration, and the radial acceleration is the square of the angular velocity times the radius, and then the magnitude of the angular acceleration, or actually, I'm sorry, not angular acceleration, but the linear acceleration is just from Pythagorean theorem and solving vectors. It's the square root of the sum of the squares of the radial acceleration and tangential accelerations. Of course, these equations are only valid when theta, omega, and alpha are all measured in radians per second and radians per second squared, respectively. We have to have everything in terms of radians because that's how we derive these equations in the first place. But as long as we have our angle measured in terms of radians, essentially we can just find the linear quantities from the given rotational quantities by multiplying the angular quantities by the distance to the point of rotation, r. It's essentially what's going on in most of these. The only difference is our radial acceleration is the only one that deviates from that, which is equal to r omega squared. It's because of the way it's defined. So just like the linear motion, it's easy to analyze rotational motion so long as we have the acceleration constant. Just like we developed the kinematic equations for linear motion when we had constant acceleration, we can develop strikingly similar equations for kinematics of rotational motion as long as the angular acceleration is constant. So if we have a fixed axis, something rotating about a fixed point with a constant angular acceleration, we have the following equations, which hopefully look like some other equations you remember from chapter 2 and chapter 3. The first one we have here is that the angular velocity is equal to the initial angular velocity plus the acceleration times the time that is accelerating, right? Hopefully this looks very familiar to you as simply omega has replaced velocity, angular velocity has replaced the linear velocity, and alpha has replaced a, so angular acceleration has replaced linear acceleration, and time has not been replaced at all because time is constant. We also have theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. This comes from x is equal to x naught plus v naught xt. That's a v naught x. Sorry about the horrible writing. V naught xt plus 1/2. This would be acceleration in the x direction or y direction, doesn't matter, times the time squared. This is essentially the same equation here, except that theta has replaced x, right? And omega has replaced velocity, and alpha has replaced acceleration, right? So essentially the same equation. As long as you can remember what to replace, we don't really have to learn any new equations. We just need to remember that the theta, omega, and alpha, what they replace x, v, and t. We also have omega squared is equal to, this is just two ways of writing the same thing, but omega squared is omega naught squared plus 2 alpha delta theta. This is completely analogous to v squared is equal to v naught squared plus 2a delta x. And then finally we have this delta theta, theta minus theta naught is a delta theta, is equal to 1/2 omega plus omega naught times time. This is simply the same that we had a delta x was equal to the average velocity times the time. We have the change in angle is equal to the average angular velocity, omega plus omega naught divided by 2 times the time. Same equation we had for linear motion. So fundamentally what we need to remember are the same equations from chapter 2, in which we have acceleration, or actually x replaces theta, or x goes to theta, v goes to omega, and a goes to alpha. So we can also talk about the kinetic energy of a rigid body that rotates about some axis here. Let's say we have this shape here, this thing here, this shape, and it's rotating about some fixed axis here, and it's rotating in this direction. It's rotating counterclockwise about this fixed axis right there. Now, if I wanted to consider the kinetic energy of just one particle on this, just this point A, if I wanted to consider its kinetic energy, I would say, well, kinetic energy is 1/2 mv squared. And v was a linear velocity, right? Remember this from chapter 7 material, that kinetic energy is 1/2 mv squared when that's linear kinetic energy. But we also know that what we defined in this lecture is that linear velocity is equal to the radius to point A, so the distance to point A we'll call RA, times the angular velocity. So the linear velocity is the r times omega, or RA, the distance to point A, times omega. So what we have is we have the kinetic energy at point A is 1/2 mass of point A, just this point A, times the velocity of point A squared, which is actually just replacing velocity of point A with RA omega. Then we just have kinetic energy of that point is 1/2 times the mass of point A times RA squared omega squared. If we were to add another point in there, because after all, we want to know the kinetic energy of all the points, we add another point in, we call that point B. Then point B has a distance to it of RB, radius to point B, and the velocity at point B is that distance times the angular velocity. And remember, the angular velocity is the same at every point on the object, right? So we don't need a subscript for the omega. Just need a subscript because it has a different distance, so it'll have a different linear velocity. So we can find the kinetic energy at point B would be, well, 1/2 mass of point B times velocity at point B squared, or 1/2 mass of point B times radius at point B squared times omega squared. If we wanted to find the kinetic energy of the entire body, then that would be the sum of all the kinetic energies of all the points, right? So I'd have to take, and I would say the kinetic energy is then 1/2 this is the kinetic energy for point A, 1/2 mass point A VA squared plus kinetic energy for point B plus the kinetic energy for point C, etc., right? And then if I redefine these the same way we did on the previous slide, I would simply say, all right, this is my kinetic energy of point A then, simply replacing VA with RA omega and replacing VB with RB omega. We get the kinetic energy of This is kinetic energy at point B, and then this would be the kinetic energy at point C, plus however many points we have. Really have an infinite number of points there. But then we see that we have a 1/2 in every term, and we have an omega squared in every term. So if I were to factor these out, then we would say that, well, this is the same as 1/2 times these characteristics of every point. The mass of point A times the distance to point A squared, plus the mass of point B times the distance to point B squared, the mass of point C times the distance to point C squared, etc. And we have all this inside here, and then times 1/2 times omega squared. This is just simply factoring here. Then we can take this and we'll define the moment of inertia as the sum of all this. All this stuff in the brackets here we'll define as the moment of inertia. So we took all this right here, defined this as the moment of inertia I, which is simply the mass of a point times the distance from the axis of rotation squared, and it's the sum of all of these for any point. And the units for this, well, mass is in kilograms and radius or distance is in meters, so it's kilogram meters squared are our units. If we just had one individual point, we would simply say that the moment of inertia is a mass times r squared. And this r isn't necessarily the radius. It's important to remember it's just the distance from the axis of rotation. So I is equal to mr squared there. So now we can write the kinetic energy in terms of the moment of inertia with that defined. And I'm not going to make you guys obviously add up a zillion points to come up with your moment of inertia. We can actually use some tables. This is derived fairly easily with a little bit of integral calculus. We can define what the mass times the for a uniform shape, or actually for even a non-uniform shape, or a uniform solid, I should say. We can find what this moment of inertia is, the mass times the distance squared of all of these. But of course we won't cover that in this class, but we have some tables that will give us that. But anyways, we can define the kinetic energy in terms of the moment of inertia by replacing all this in the brackets with I, so that we get the kinetic energy of a rotating body is equal to 1/2 I omega squared. Now, the difference in kinetic energy between linear motion and rotational motion is that, well, in linear motion, I just took the whole entire mass, and then every point on that mass had the same linear velocity, right? So it's very straight, mass times velocity squared, very straightforward. Now, in rotational motion, since the linear velocity depends on how it's positioned about its axis of rotation, we have to consider not only the mass of the object, but how that mass is distributed away from the axis of rotation. So we have really, it's the same equation, except we have, instead of mass, we have I. So we have the moment of inertia here, which considers how the weight is distributed about the axis of rotation. And we also have, instead of a linear velocity, we have the square of the angular velocity. But essentially, the form is the exact same as the form we had for kinetic energy for linear motion. We're just simply replacing the mass with the moment of inertia and the velocity with the angular velocity. But this is K is equal to 1/2 I omega squared is your kinetic energy of a rotating body. So I said that your book gave us a table, so we didn't need to do any of the calculus involved or geometry involved in finding the moments of inertia. And this table is table 9.2, given to you on page 279 of your textbook. Now, the important thing with the moment of inertia, as I pointed out in the previous slide, is that the moment of inertia takes into consideration how the mass is distributed about the axis. Well, of course, if we are going to talk about how the mass is distributed, then we better talk about, which axis we're talking about, right? Or we better know what axis we're talking about. So you can look at these two cylinder rods. They have different moments of inertia. One of them is 1/12 ml squared, one of them is 1/3 ml squared. The reason they have a different moment of inertia is because you look at where the axis of rotation is. You see that one of them has an axis of rotation through its center, and another one has an axis of rotation through its end right here, right? And so they have different moments of inertia because of the way that the mass is distributed. And it might seem sort of interesting. Take a look at how the moments of inertia differ. One of them is actually, 4 times as much. 1/3 ml squared is 4 times as much as 1/12 ml squared. And why is it that it's 4 times as much? Remember, moment of inertia was defined as the mass times the distance away from the axis of rotation squared. If my axis of rotation is in the center, then the furthest distance away would be L/2, right? This point out here on the end is L/2. And if my axis of rotation is at the very end, then I have a full distance of L, right? So in B, in the cylinder rod with the axis through one end, the distance to the mass is twice as much as it is in case A with the cylinder rod whose axis is through the center. So if the distance is twice as much and we have in the moment of inertia the distance is squared, then it would make sense that the moment of inertia is 4 times as much. So that's why this actually makes perfect sense that the moment of inertia is 4 times as much when the mass is distributed twice as far away. Same thing, we can look at this plate here, rectangular plate. The axis is through the center. Well, the way the weight is distributed depends both on A and B. And actually, you can see that maybe this is based off of Pythagorean theorem a little bit here, how the mass is distributed. And we see that mass, or that moment of inertia, is 1/12 mass times A squared plus B squared. Of course, if we look at the same rectangular plate with a different axis of rotation, we see that actually this length B doesn't really matter, because it doesn't really matter how long it is, because we're only concerned about how far away it is from the axis of rotation. So the only dimension that comes into play is actually A, because that's the only one that dictates how far away the mass is from the axis of rotation here. Similarly, you can see with these cylinders, we have a couple different types of cylinders. We have 3 cylinder types down here. A hollow cylinder is like a donut. It has an external radius, we'll call R2, and it has an internal radius, R1. And both of these would play a role in how the mass is distributed. So we get a moment of inertia dependent on both of those. If we have a solid cylinder, then we can figure out what the moment of inertia is just by knowing the external diameter. And if we have a thin-walled hollow cylinder, then this means that let's compare these two. Let's compare F and G, the solid cylinder and the thin-walled hollow cylinder. If they have the exact same mass, not looking at the moments of inertia up here, I'll block these out for you for a second. If we don't look at or if we say that they both have the same mass, then which one would have a higher moment of inertia? Well, if it's a thin-walled hollow cylinder, and it has the same mass, that must mean all of its mass is at the outside edge, right? So having all of its mass at the outside edge, and then the distance to that mass is squared, it would make sense that the moment of inertia is higher if all of its mass is further and further away, right? So that's actually exactly what we have here, and it works out that a thin-walled hollow cylinder has twice the moment of inertia of a solid cylinder when they have the same mass. And we can see that we actually have the same relationship hold true for a solid sphere versus a thin-walled hollow sphere. If they have the same mass, then the thin-walled hollow sphere has a higher moment of inertia than the solid sphere does. And that pretty much brings us to an end for Chapter 9 material. Check La Lima for example problems.